Hello, dear friends. So in this lesson, we're going to learn the difference between classification and regression. So let's get started. Supervised learning is the most common type of machine learning because it is much easier to train a machine to learn with labeled data than with unlabeled data. So in other words, depending upon what we want to predict, supervised learning is used to solve two types of problems: regression and classification. So now let's consider them separately and start with classification first. So classification is simply a way to distribute data between the various classes defined on a data set. Classification algorithms learn this distribution form from the given training set and then try to classify correctly. In the classification, the group membership of the problem is defined. The data is categorized under different labels according to some parameters, and then the labels are estimated for the data. So if there are two classes, this is called binary classification. If there are more than two classes, it's known as multi-class classification. All right, so now let's talk about regression. Regression is the prediction of the behavior of a random variable using a model. For example, let us have a model trained with a data set. So with this model, we can predict a value that we want to learn or another value that corresponds to a value. This process is called regression in statistical science. Basically, regression calls a relationship between two or more variables. So the task of measuring the level and scope of this relationship is called regression analysis. It's necessary to obtain the relationship between parameters as a function. Now, parameters can be independent or interdependent of each other. So, my friends, that's the evaluation of regression and classification. So let's dig into some of the differences now. So some of the main differences between classification and regression. The main difference between classification and regression is while a categorical variable tries to estimate in classification, for example, patient or not patient, 0, 1, a continuous value is attempted at estimation in regression, for example, car or house prices. While classification predicts unordered data, regression predicts sequential data. Now, another difference is evaluating the performance of each. So while classification is evaluated by measuring techniques such as accuracy and precision, a regression can be evaluated using mean square errors. All right, so there you go, regression and classification. In the next lesson, we're going to learn about the criteria used to evaluate them and how to interpret all of that. So until then, have a nice day. Well, hello, my dear friends. So in this lesson, we're going to learn performance classification of classification error metrics. All right, let's get started. So what are these classification metrics and how are we going to be using them? Now, the key classification metrics that we should understand are our accuracy, recall, precision, and F1 score. So first off, we should understand the reasoning behind these metrics, and also that'll give us a clue as to how they actually work in real life. So typically in any classification task, your model can achieve two results. Either your model was correct in its prediction or your model was incorrect in its prediction. And pretty much all classification metrics originate with this idea. Fortunately, incorrect versus correct also expands to situations where you have multiple classes, such as trying to predict categories of more than two. For example, you have categories A, B, C, D. Well, you may be correct in guessing the correct category or wrong in guessing the correct category, right? All right, so let's continue on with the metrics. So this is simply known as binary classification, all right, which just means binary, really. There are only two available classes, yes, either class 0 or class 1. So this idea is going to expand through multiple classes as well. But for our purposes and to simplify it, let's just imagine a binary classification situation. So in our example, we'll try to guess whether an image is a lion or a tiger. Now, as this is a supervised learning problem, the first place we need to do is build or train a model on some training data. This means we're going to have images where a person has gone before and has been tagged as a lion or a tiger. Then we'll test this model on test data. So we're going to show new images that the model hasn't seen before. Take the model estimate and then compare the results of the model estimate with the correct answer that we already know. Hence, when we have model predictions from X test data, we compare it with actual Y values. So let's actually diagram this process out. Now, supposing that we have already trained our model on some training data, and now is the time to really evaluate the performance of the models. So this is where our test data set comes in. All right, so we get a test image from where we will tag the X test, X meaning feature. So the actual image itself is a feature, and there is a corresponding correct tag from this test set and test Y. So we have the X feature or image and this test image, and also we have the correct label from test Y. And in this case, we can see that this image is an image of a lion. So we'll just feed the features. The image, in this case, is already trained to our model. And then the model is going to make some prediction. So the model predicts that this is a lion. And then what we do is we compare the prediction to the correct label. So this lion equals lion, and it's correct in this case. But maybe it guessed this image was a tiger. And in this case, this comparison with the correct label would be wrong. And these are actually just two cases. Of course, you're either right or you're wrong, correct or incorrect. So then we repeat the process for all images in our X test data. And then eventually, we'll have the count of correct matches and the calculation of incorrect matches. And the main difference that we have to make here is that not all false or correct matches are of equal value in the real world. So why don't we focus a little bit more on what we mean by all this? So in the real world, a single measurement won't tell the whole story. To understand it all, let's bring back 4 metrics that we mentioned and see how they actually calculate. So we can arrange our predicted values by comparing them with real values and what's known as the confusion matrix. So we'll touch upon the confusion matrix a little bit later on, but let's talk about accuracy first. Accuracy is one of the most common classification criteria. Fortunately, it's easy for us to understand. So it's really intuitive what it's measuring, right? So in classification problems, accuracy is obtained by dividing the number of correct predictions made by the number or total number of predictions made. So, again, it's the number of correct predictions divided by the total number of predictions. How many guesses will you get correct, and what's the percentage? For example, suppose that the X test set is 100 images, and our model correctly predicted 80 images. Well, we've got 80 divided by 100, or 0.8, or 80% accuracy. Right, and the accuracy is really useful when the target classes are well balanced. And what does that mean? Well balanced, well, in our example, this means that the actual tags are represented roughly equally in the data set. But let's imagine that we have what's known as an unbalanced class case. So basically that means that the actual labels themselves are roughly equally represented in the data set. Let's imagine that we have what's known as an unbalanced class situation. So in this case, accuracy is actually not a good metric to use. So let me take you through a little thought experiment. Let's imagine that in this test, we had 99 images of lions and only one image of a tiger. Now, if our model was simply a line that just always predicted lion, no matter what the image it saw was, then we would actually get 99% accuracy with this particular test. Because by 99 images are lions and one image of a tiger, well, it only missed one. So, you should be aware of the downside of accuracy. And this downside will arise when you really have an unbalanced class situation. So if your classes are roughly balanced, accuracy is a very nice or intuitive method or metric to understand. However, if you have an unstable class, you may find that it starts to represent a problem in this particular case. And that's where these other metrics come in. So again, in this case, you'll want to understand recall and precision. That helps us understand how well it performs in unbalanced classrooms. Recall is the ability of a model to find all relevant cases in a data set. And the exact definition of recall is the number of what are known as true positives. And we'll focus on that later on when we see the confusion matrix. But it's the number of true positives divided by the number of true positives plus the number of false positives. And precision is the ability of a classification model to identify only the relevant data points, where precision is defined as the number of true positives divided by the number of true positives plus a number of false positives. So often you have a trade-off between recall and precision. While recall expresses the ability to find all the relevant instances in a data set, precision expresses the proportion of the data points our model says was relevant that actually were relevant. And then there's the F1 score. So this is essentially a combination of the both of them. So in cases where we want to find the optimum mix of sensitivity and recall, we can combine the two metrics using what is known as the F1 score. The F1 score is the harmonic mean of the precision and recall that takes both measurements into account. So this is not just averaging the recording position, you get it? But actually taking their harmonic average. So the reason that we use harmonic average instead of a simple average is that it will penalize extreme values. For example, if you create a classifier that had a precision of 1, meaning essentially perfect precision, and a recall of 0, meaning essentially the worst recall possible, if you were to just take the simple average of this, then it would be 0.5. But the F1 score, because it's taken a harmonic average, we have precision times recall there at the top, which means you get 0 times 1 of the top, and you get an F1 score of 0. So this is really nice because it allows you to punish the extreme differences between precision and recall. So basically it gives you a fair assessment of this trade-off between precision and recall. So we can now view all correctly classified and misclassified images in the form of a confusion matrix as well. All right, so are you ready for the confusion matrix? It looks something like this. So we have the right underlying conditions. This is the correct label. And we can actually think of the situation as positive or negative, such as being a lion or not being a lion. Or It's often used in medical diagnosis, such as the presence or absence of disease. Well, we have the presence of disease, and then we have patterns in which the condition is predicted. You follow? So the forecast is going to be a positive or negative guess. And when it comes to confusion matrices, I think it's easiest to get an intuition first if you think of it as a diagnostic test for some kind of disease to be present in a person. So you run it through your model. For example, a true positive might be that someone actually has that disease, and your model accurately predicts that they have the disease. A true negative is that someone doesn't get the disease, and your model accurately predicts that they don't have the disease. So there are true positives and true negatives, and these are both correct predictions. And then we actually have these two types of false predictions, one false positive and one false negative. If the person does not have the disease, it will be a false positive, and you predict that they do not have it. That is also a positive. Because you're wrongly saying that they're positive for their disease or condition. A false negative is essentially the opposite of that, where this person does have the disease present. So if you report back using your model and your test that it's actually negative, well, they don't actually have this disease. These are sometimes referred to as a type 1 error and a type 2 error. And then, based on these essentially true positives, true negatives, and false positives, there are many other metrics that we can calculate. So as we can see, the actual calculation for accuracy in the lower left-hand corner, we can see some here, and that's the sum of the true positives plus the true negatives. Essentially, out of the total population, it is the sum of the correct ones. And there's a bunch of other ones like positive likelihood ratio, false positive rate, true positive rate, prevalence true discovery rate, and many more. But now the main point here to take away is the confusion matrix and the various computed metrics are basically the main ways of comparing the predicted value with the actual value. And what constitutes good metrics actually really depends on the specific situation. All right, so now a very specific question for you. Is that good enough accuracy? Well, it really does depend on your situation and the context of the situation. But now, if you're still confusing the confusion matrix, it's really no problem. Check out the Wikipedia page for it. It's got a really good diagram with all the foremost for all the metrics. So now I want to go back to the first question. Is that a good enough accuracy? And as always, this really depends on the context of the situation you're running your model in. There's no single number I can give to say something like 90% accuracy is good enough for every situation, right? We've already seen the topic in unbalanced classrooms, but there is no really good explanation for what it is with a good enough precision or recall. And we need to think about the context of the situation. So let's rethink the diagnostic model to predict the presence of a disease. So if we have created a model for predicting the presence of disease, the first thing that I want to think about is, are we going to have balanced classes or unbalanced classes? So the presence of disease in the general population is well balanced and is almost unlikely in most cases. There will probably not be a disease in which about half of the population is affected and half the population is not affected. So we can already tell that we're going to have an unbalanced class situation where this means that we're not going to have a precision recall trade-off. Therefore, we should not forget that these models are often used as rapid diagnostic tests that must be done before having a more invasive test. For example, for prostate cancer models, it's very common to do a simple urine test before taking a biopsy because it's much easier to have your urine tested than to do a complete biopsy of the prostate, yeah? So we also need to consider what's at stake. If it's prostate cancer, the risks are actually quite high. So as we mentioned, we often have a precision recall trade-off, which means we have to decide whether the model will focus on correcting false negatives versus false positives. So at the expense of reducing false negatives, we'll likely increase false positives, and vice versa. And it's probably better to try to minimize the number of false negatives at the expense of increasing the number of false positives when you're talking about disease diagnosis. So it goes in the direction of false positives. And why do we actually want to do that? Well, because we want to make sure that we correctly classify as many cases of the disease as possible. Therefore, we are doing our best to reduce false negatives at the expense of increasing false positives, right? Why would we actually want to do that? Well, in fact, we want to make sure that this disease exists, or anyone with prostate cancer in this example. If we're doing a urine test, we want to make sure that all these people exist. The disease will actually go to the next step. That is perhaps a more invasive test, like a biopsy. And remember, this kind usually comes at a cost of increasing those false positives. So we can see for something as important as disease diagnosis, really minimizing those false negatives becomes really important. And pretty much all of this is to say machine learning is not going to be performed in a vacuum. And these performance metrics don't have some kind of universal truth that applies to all problems. But machine learning is truly a collaborative process where we must always consult experts in the field. For example, in the case of disease diagnosis, we should probably be talking to doctors as far as what our acceptable standards for false negatives versus false positives are. And this is going to change depending on the context of your situation. So just always keep this in mind. For me, it would not be an easy answer to say that this is a good enough accuracy or precision or recall, because it all depends on the context and scope of the situation. All right, so that is I'd say an introduction or a brief overview about how we can evaluate classification models. Of course, the more you evaluate, the more evaluation will be done. So we'll go ahead and we'll move on to the next lecture because we're going to discuss evaluating regression tasks. All right? So I want to see you there. Well, hello, dear friends. So in this lesson, we're going to learn the error metrics. All right? So let's get started. Now, in general, when a model constantly tries to predict values, it does this as a regression task, as opposed to classification tasks where we try to predict categorical values. Therefore, as we just said, you may have heard some evaluation criteria such as accuracy, recall, or precision. Well, these sort of metrics aren't going to be very useful for regression problems. So it doesn't really make sense to calculate the accuracy or recall of a regression task because you're actually classifying things. Instead, you're predicting a continuous value. So that means we need new metrics designed for those continuous values. For example, Imagine trying to estimate the price of a house based on its features. Well, this would be a regression task. Or it may be trying to predict the country in which a home was located, given its characteristics. Well, that would be a classification task. Okay, so now we're going to focus on how to evaluate this regression task where a tag is continuous and not separate categories. So moving on to discuss the most common evaluation metrics for regression, which are mean absolute error, means squared error, and then root mean square error. So let's begin with the simplest, which happens to be mean absolute error. And, well, perhaps it's the easiest to understand, so let's lay it out. Basically, all you have to do is compare and remember your predictions. So here we're comparing a continuous value because this is a regression task, and we will compare our predictions with the true Y label. For example, compare the actual prediction of the house price with the true house price. And then what we do is just take the difference between the true price minus our predicted price. And you see, that's why we take the absolute value of that. And the reason we take the absolute value is because technically our predictions could be over or under the true value. And since we want averages across all our predictions, we will take that absolute value. Okay, so this is basically the mean absolute error. You just get the differences between your prediction and the true label, and you get the absolute value of that, and then you get the average of all of your predictions. Now, there is an issue with mean absolute error is it won't punish large errors. So here we have something known as the Anscombe's quartet. And here we can see that we have a wide variety of different distributions of data points. However, the line of best fit for all of these is actually the same. So you see why we want to make sure that we're aware of these kind of situations. So let's take a look at this particular case, for example. So here we have a point that is a big outlier, right? So we want our error metrics to really take these into account. So what we can do is actually use the mean square error, and this is the mean of the squared errors. So what we're doing here is we're going to take the difference between the true value minus our predicted value, and then we're going to square it. And when we actually take this square, as you can guess, that larger errors are noted more than the mean absolute error. So this makes the square error a bit more popular because you're going to actually penalize your model for those outliers where it's just not suitable. And we don't need to take absolute value anymore because everything that is square is positive. However, there's an issue that we run into with mean squared error. This is the squaring of the actual label minus its prediction. Actually, also squares the units themselves. So, for example, if you're predicting the price of a house, then our error metric with mean absolute error would be in dollars, but with mean squared error, we end up getting an error metric in units of dollars squared. And, well, I haven't checked my bank account today, but I think that's pretty difficult to interpret. So, the way that we fix this is with the root means squared error. So essentially, at the end, you just take the square root of your mean squared error. So this then becomes the most popular because it penalizes both larger error values and has the same criteria or the same units as Y at the end of the day. Okay, so let's continue the most frequently asked question. Is this root mean square of the error value any good? Well, as always, context is everything. Okay, so now suppose you're implementing some kind of machine learning model and you get a $20 root mean square error. And then you ask me, is this root mean squared error, well, is it good enough? And again, I got to reply, well, it really does depend on the context of the situation. And you get that, right? Context is everything here. Because if you're predicting the price of a house because it is $20 smaller than the average price of a house, root mean squared error, $20 error, well, that's really good, yeah? However, if your machine learning model needs to estimate the price of a chewing gum, let's say, based on its features, and the root mean squared error is $20, whoa, that could put everything out of whack, right? So what we need to do here then is compare your error metric for the regression task to the average value of the label, which is the average value in your data set, and then you'll be able to try to get an insight into its overall performance. Make sense? And as always, domain knowledge also plays a really important role here. So again, machine learning is not done in a vacuum. It's usually done as a collaborative process. So if you're predicting the prices of a house and you want to get an idea of whether your root mean squared error is good, probably it's a good idea to start talking to someone with experience, like, I don't know, real estate agent? Okay, obviously it's just an example, but you get the point. So here we've learned a few different metric sets that you can use to evaluate the performance of a regression task. That's it for this, and I want to see you in the next lesson. Hello, dear friends. Welcome to the machine learning of Python. So, now that we've had an introduction to machine learning, in this tutorial, we're going to discuss how to use Python and the Scikit Learn package to perform machine learning with Python. Sounds pretty good, huh? So let's get started. Scikit Learn package. Now, that happens to be the most popular machine learning package for Python, and it has a lot of algorithms already built into it. You'll need to install it in your command line or terminal using conda install scikit-learn. Now, if you have an Anaconda distribution or another distribution in Python, you should write !pip install scikit-learn in your command line. Okay, so let's talk about the basic structure of how to use scikit-learn. Well, first, we need to back up a little bit and review the machine learning process. But just briefly, don't worry. So the machine learning process starts with your data. You have to acquire data somehow, and then the next step is usually to clear and format that data. So then the machine learning model can accept this before you give it to the machine learning model, right? And as part of that process, by clearing this data, you will split it into a test set and a training set. Train your model or training set. And then in the next step, test your model in the test set and repeat your model and adjust the parameters of your model until you're ready to deploy. All right, so now let's do an example using scikit-learn. Now, I don't need you to worry about memorizing any of these. You will see these steps over and over and over again, and we'll guide you through each of these steps. So just hang on for the ride. In fact, we're actually coding out the algorithms. So remember, this here we're doing is just an overview, and this will make it very familiar for you when it's time to be coding it out. Okay, so every algorithm in Scikit is exposed via an estimator object. You will first import the model, and the general form of this is to say from sklearn.family import model. So as a specific example, it would look like this. Let's say that we want to perform a linear regression, which will be the first machine learning algorithm that we learn. We'll go ahead and say from sklearn.linear_model, where it linear underscore model is the family of models. Import, and then linear regression. And that linear regression is that estimator object, and that's the model itself. And then the next step would be to embody this model or estimator. So all parameters of an estimator can be adjusted when they all have appropriate default values. And then we will explore these values and these parameters using Shift-Tab in Jupyter Notebook. Check all possible parameters. For example, you can start a linear regression model by simply specifying a parameter as normalize equals true, and then after printing the model you just instantiated, you can go ahead and check the parameters such as intersection true and copy x equals true, which is the default for the model. I actually don't need to specify normalized as equal to true because these are additional parameters that you can use to tune the model to something more specific. So after your model has created your parameters, it's time to fit your model to some data. But keep in mind that we need to split this data into a training set and a testing set. So I'll make an example here of how we can do just that. So I'm going to go ahead and say import NumPy as NP in order to create some fake data. And then we can use Scikit learn to do train test split, splitting our data into training set and testing set. And then we're going to say from sklearn.model underscore selection import train underscore test underscore split. Then we're going to have our sets of data, X and Y. X being the actual features and Y is the actual label for each of those feature rows. And then using train test split, you will pass in X and Y. And you will pass in the test size. Now, again, don't worry too much about memorizing or fully comprehending everything here. We have a lot more practice later on with this process. But I just want to give you an overview so you can use train test split on your features and labels. And Scikit learn will automatically output your training set and your testing set. All right, so we have X train and Y train and X test and Y test. And of course, you can see how these arrays are outputted here. All right, so basically you have attributes for your training and test data, as well as labels for your training and test data. So now that we've split the data, we can train or fit our model on the training data. And this is done through the model.fit method. So basically, you take your model. Now remember how we embodied it as a linear regression estimator. And then you can say model.fit and pass in your training data. And then you pass in your X training data, which are the features of your data. And then you pass in your Y training data, which are the training labels. All right, great. So now you see how the model has been fit and trained on the training data. And this makes the model ready to predict labels or values on the test set. Again, remember I'm showing an example of a supervised learning process. The process for an unsupervised model is going to be a little different because you're actually not going to be having these labels. But every supervised learning model will get the predicted values using the predict method. So we'll just go ahead and say model.predict. Pass in your X test data, and those are your test features, and you get predictions from that. So here's where you can evaluate the model by comparing the predictions with correct values. So the evaluation method depends on what type of machine learning algorithm you are using. Different evaluation methods, of course, are used for regression versus classification versus clustering, and that goes on. But we'll go ahead and we'll just get a quick summary of all this. Scikit-learn, really strives to have a uniform interface across all methods, and we're going to see some examples of that below. So given a scikit-learn estimator object named model, these following methods are available. In all estimators, you're going to be able to fit to the training data. Then for supervised learning applications, this will be X and labels Y, except for 2 arguments. For unsupervised learning applications, this only accepts a single argument. The data which makes sense because unsupervised learning works on unlabeled data, right? Okay. Now, available in supervised estimators, you're going to have a predict method which, given a trained model, is going to predict the label of a new set of data. So this method accepts 1 argument, the new data, which is going to be X_new. So in this example, or in the previous example, it was X_test. And then this returns the learned label for each object in the array. Great. So also available in supervised estimators is the predict_proba method. And then for classification problems, some estimators provide that method, which returns a probability that a new observation has in each categorical label. So in this case, the label with the highest probability is returned using the model.predict method. For classification or regression problems, you also have a score method available, and in most estimators will implement this method, and scores are between 0 and 1, with a larger score indicating a better fit. Also available in unsupervised estimators is the model.predict. And of course, that will allow us to predict labels in clustering algorithms, and again, that's in unsupervised estimators. But also, when you're given an unsupervised model, you'll also have the model.transform method, where you can transform new data into new bases. Now, we'll, of course, go into much more when we talk about unsupervised learning algorithms later, but basically, this also accepts 1 argument, X_new, and returns a new representation of the data based on the unsupervised model. And again, I don't want to jump the gun here, but I just want to contrast the differences here. We're going to dig way deeper into that topic, and I'll explain it in a lot more detail when we talk about unsupervised machine learning problems. But there's one more thing here, and I want to point this out, that there is the model.fit_transform for unsupervised estimators. Now, some estimators apply this method, which performs a fit and transformation on the same input data, just more efficiently. All right. So now you might be wondering, well, okay, so how do I choose an algorithm classification versus regression versus clustering? Well, if you go ahead and just write scikit-learn algorithm cheat sheet in your Google search bar or wherever you want, you're going to get a picture like this. And this is from the official scikit-learn documentation. But basically, this is a bit of a decision tree or a guide on how to choose an algorithm. And if we go ahead and start, you'll see that it has asked you more than 50 examples. If not, you really should get more data. So if you don't have more than 50 samples, then it asks you, are you trying to predict the category, predict the quantity, whether the label is data, etc., right? Okay, my dear friends. So we're going to start Python for machine learning by launching our first machine learning algorithm, which will be linear regression. All right. So thank you very much, and I want to see you in the next lesson.